Assalamu alaikum. Dear students, today we shall talk about the oxidations of different organic compounds using lead tetraacetate. Now, what is the structure of the lead tetraacetate? It has a square plane structure. So, four acetoxy groups are attached to lead. What are acetoxy groups? You may also write it like here, like that. Acetyl group. Four acetyl group are attached to the lead. So for simplicity, we write it like this. But you may also write its structure like this. Lead tetraacetate. it the main applications of lead tetraacetate in oxidation reaction is that it cleaved the carbon-carbon single bond in 1,2-diols. Although it has many other applications, but the main application of this oxidizing agent is the oxidative cleavage of 1,2-diols, the same that we studied a couple of lectures ago, that the oxidations of 1,2-diols using sodium periodate or iodic acid. So this reagent also cleaved the carbon-carbon single bond in 1,2-diols. This reagent also can be used for the oxidations of alcohols. Not only 1,2-diols, dihydroxyalkanes, but also it could be used for the oxidation of alcohols. It can be used for the oxidation of keto acids, or more simply alpha keto acids. It can also be used for the oxidation of alpha keto carbonyl compounds. The last application that we will study for the lead tetraacetate is the decarboxylation of dicarboxylic acids. Decarboxylation of dicarboxylic acid. So one by one we will study the applications of the lead tetraacetate as an oxidizing agent in the oxidative cleavage of 1,2-diol. So let's first start with the oxidation of 1,2-diols. This is cyclohexane 1,2-diols. When it is reacted with lead tetraacetate in the presence of DCM or carbon tetrachloride, the bond carbon-carbon bond between the vicinal carbons, it is cleaved, it is broken by lead tetraacetate, and we get this aldehyde diol. Now let's first discuss the mechanism, how this occurs. Mechanism. few minutes ago I wrote the structure of lead tetraacetate. I'm writing the same one. What happens in the first step? In the first step, these two hydroxyl groups, which are vicinal to each other, it attacks on this and it leaves this oxygen gets the positive charge minus OAC. One of the acetyl group it leaves, leaving behind the three others attached to the lead. What happens in the next step? Since the oxygen is now positively charged, deprotonation occurs to get some stability. Since the electronegative element bearing positive charge is considered highly unstable, to get stability it pulls the pair of electron towards itself, making it neutral, and hydrogen gets the positive charge. And this hydrogen now bears positive charge, it react with this acetoxic group. So then you in the better way, this acetic acid, one molecule of the acetic acid leaves, and you get this one. In the next, since we have another OH group, it attacks here and it leaves oxygen, now gets positive charge minus OAC. In the next step, the same in the previous way, uh, deprotonation occurs, and when this deprotonation occurs, hydrogen ion or proton leaves, and this proton reacts with this leaving acetate ion, so both forms the acetic acid. So acetic acid, molecule of the acetic acid leaves, and finally you get this cyclic intermediate. Cyclic intermediate is obtained. In the next step, this cyclic intermediates, this ring, the cyclic intermediate, it ruptures. How this rupture occurs? This bond moves here. This is very important, the rupturing of this cyclic ring. So I'm going to show it by red arrows that this bond moves here, this bond moves here, and this bond moves over lead. When this bond moves here, making carbon oxygen double bond, this bond that is attached between two adjacent carbon atoms, it cleaved. No bond will remain here, and this bond will move here, making another carbon double bond oxygen, and this bond will leave. The pair of electron will go over the lead. So you will get carbon double bond oxygen here and the hydrogen here. Similarly, carbon double bond oxygen here and hydrogen here. So you will get now two molecule of two functionalities of the aldehyde group. and lead diacetate leaves. Now lead here has the +2 oxidation state, while in the start it had +4 oxidation state. It means it has reduced, so it has oxidized the other compound. So in this way, 1,2 diols, in this way, this 1,2 diols, they undergoes oxidative cleavage, and each alcoholic functionality changed into carbonyl functionality. I'm going to write here another structure for your better understanding. What happens if I had methyl here, OH, lead tetraacetate, LTA, in the presence of DCM? What would be the reaction? We know that lead tetraacetate actually cleaved the this carbon-carbon bond that has two hydroxyl group adjacent to each other. So these are 1,2 diols. Oxidative cleavage will occur, and each hydroxic functionality will change into carbonyl functionality. So your final product will be this one. Now question arises that why do we use lead tetraacetate? The same type of reaction could also be carried out using this one, iodic acid, HiO4, in aqueous media. So why do we carry out this oxidative cleavage of the 1,2 diols using lead tetraacetate? So students, this is very noticeable that actually periodic acids is usually used for those 1,2 diols which are water soluble. Do you remember that last time we studied the glucose, we studied the oxidative cleavage of the glucose and fructose, these carbohydrate and glyceraldehyde. Such carbohydrates are water soluble, but how would we carry out the oxidations of the 1,2 diols for those compounds which are not soluble in water but they are soluble in other organic solvents? So for those compounds that are insoluble in water but are soluble in other organic solvents, there we will use this lead tetraacetate for the same reactions that we studied last time for the oxidative of the 1,2 diols with periodic acids. Here I am drawing another molecule. Now what would be the products? In the previous examples, the two hydroxyl groups were on the same site, were on the same phase of the carbon-carbon single bond. So you may say it as a syn dihydroxy compound, but here the two hydroxyl groups are on the opposite phases. They have the phase difference. So these are trans to each other. know what would be the product. Remember, the product will be the same because lead tetraacetate reacts the two vicinal diols in the same way, whether they are syn to each other or they are anti to each other. So your product will be the same. But remember that there will be the difference of the rate of reactions. The rate of reaction for those vicinal diols which are on the same phase, on the same side, they react considerably in a faster way as compared to those where these two reacts, where these two, if they are present on the trans side, they react slowly. Now I'm writing another important reaction where this oxidative cleavage of 1,2-diol is going to occur. This is decalene system where 9-10 positions have two hydroxyl group and they are vicinal to each other, and both of them are going to react with lead tetraacetate. Now I'm not going to describe the whole mechanism. My question is, DCM is a solvent, non-polar solvent. My question is that which of these two reactions will occur relatively faster way? Which is the rapid reaction among these two? To find the answer, you will have to write its chair structure. In when they are on the cis side, these two will be pointing upward. For the trans-decalene system, these two OH are pointing opposite to each other. This hydroxyl is pointing upward direction and this hydroxyl is pointing in the downward direction. And both of these hydroxyl group will form a cyclic intermediate. But the cyclic intermediate that will be formed from these structure where two hydroxyl group are on the same side, it is relatively easier to be formed and without any statically strained structure. This intermediate will be formed, and when it reacts, the intermediate will be formed, but that intermediate will have a considerable strain in it. So you see that here there is considerable strain exist that actually find itself difficult to be formed. So this intermediate is formed relatively faster. So there will be a faster reaction. What happens in the next step? There will be cleavage. I will show this cleavage with black marker. Now, what will be the product? The product would be the same in both cases. You will get the oxidative cleavage at 9-10 positions. You will get the same compound, but there is the difference in the rate of reaction, and you will have to understand the reason. I'm going to repeat it for you, that in the cis decalene system, the formation of the cyclic intermediate is quite easy. So the formation is relatively easier. This intermediate has no strain itself. So what will happen? The cleavage will occur faster, and you will get the oxidized decalene in a faster way. While in the transdecalene, there is a considerable strain in the formation of the intermediate using lead tetraacetate. So that's why the formation is slow, and it also reduces the rate of reaction. I'm leaving for you a problem. You will have to find the answer. You'll have to write it down, and you will have to tell me on the on the WhatsApp. So what these two molecules, upon oxidation with lead tetraacetate, what will be the product? And among these two, between these two, which molecule will undergo faster oxidation upon reaction with the lead tetraacetate? You will have to solve it by yourself, and you will have to tell me the answer. Now we will discuss the second application of this lead tetraacetate, that is the oxidation of alcohols. Previously we studied the oxidation of the 1,2-diols using lead tetraacetate. Now we'll study the oxidation of alcohols. The alcohols, upon oxidation with lead tetraacetate, they are changed into either aldehyde or the ketone. If you have the secondary alcohol, so upon reaction with lead tetraacetate, you will get a ketone. And the same way, if you have a tertiary alcohol, under the ordinary conditions there will be no reaction. Now what is the mechanism of this reaction? Mechanism. We know that primary alcohols, they have the hydroxyl groups in them. I'm writing an example, a general structure of a primary alcohol. It is going to react with that tetraacetate. What happens? It acts as a nucleophile and attacks on the nucleophilic center, which is highly lectin deficient. This leaves what will happen in the next step, deprotonation will occur. Here we have leaving OAC, this the leaving acetyl acetoxy group having negative charge on it. The first step is the attack of the alcohol on this lead tetraacetate. How? This hydroxyl group, through this oxygen, it attacks on this lead acetoxy or acetate ion. It leaves, since the oxygen gets positive charge, deprotonation occurs. This proton leaves and this oxygen is now neutral. You get this intermediate. In the next step, this acetate ion which lived in the previous, it abstract the alpha hydrogen. So here you will write abstraction of alpha hydrogen. This bond will move here, making a new bond between carbon and oxygen. This will leave like this. I will show here with the black line. So when this acetate ion, it abstract this alpha hydrogen, this bond moves here, making a new bond between carbon and oxygen. Now already it has single bond. When another bond will occur, so carbon double bond oxygen will take place, and this bond moves here. So acetate ion, one of the acetate ion will have to leave to get the stable species. So you get lead acetate, not tetraacetate, no, lead acetate. Here you have aldehyde and some molecules of the two molecules of the acetic acid. So you see that primary alcohols form aldehydes. So if you will have secondary alcohol, you will get a ketone. And why the tertiary alcohols are resistant toward oxidation? Since they don't have alpha hydrogen, so the reaction does not proceed further. Only the reaction stops here, the formation of the intermediate. But since there is no alpha hydrogen, so no reaction will occur. So the mechanism of the secondary alcohol with lead tetraacetate and the formation of the ketone in return, so you will have to try the mechanism by yourself. It's quite easy. I'm sure that you will be successful. If the alcohols have gamma or delta hydrogens, if alcohols have gamma or delta hydrogens, so this is delta, sign of the delta, and this is gamma, then what will happen? this is alcohol, and it has gamma as well as delta hydrogen, alpha, beta, gamma, delta hydrogen. So upon reaction with lead tetraacetate, we get cyclic ether. Cyclic ethers are formed. How? Let's see the mechanism. We know that when alcohol react with 1 2 3 4 1 2 3 4, so when alcohols react with lead tetraacetate, the same as we discussed in the previous way, that primary alcohols, they changed into aldehyde through this mechanism. So the same reaction will occur. So this carbon will change into an aldehyde. One hydrogen will be here. 1 2 3 4, alpha beta gamma. I'm writing this again, this molecule again. The aldehydes, if they have gamma or delta hydrogen, what happens? The acetate ion that left during the mechanism from the molecule, it abstract the alpha beta gamma hydrogen, abstraction of gamma hydrogen. What will happen? This bond will leave here. You will get negative charge, CH2, CH2, C, double bond O here and here. Now this carbene ion, it attacks over here, and this bond moves here. Do you see that although it was a primary alcohol, upon oxidation with lead tetraacetate, it changed into an aldehyde? But these long chain aldehyde are not so stable. The open chain aldehydes are not so stable. If they have gamma or delta hydrogen, they most likely to be converted into a cyclic form, cyclic structure. So when aldehydes are formed, the acetate ion are present in the reaction mixture. They abstract this hydrogen, and upon the abstraction of this hydrogen, the bond moves, the pair of electron moves over this carbon, making it carbene ion, and this carbene ion rapidly reacts because the electrophilic center also exists in the same molecule. So when it sees the partial positively charged carbon atom, so it rapidly reacts on this, and this bond moves over the oxygen, and you will get this. I will write another time, so you can understand in a good way. So when this carbene ion is there, it attacks on this carbon, this bond moves here. So what will be the ring size? How many carbon atoms would be there in the ring? 1 2 3 4, How many bonds would be there? 1, 2, 3, 4. 4-membered ring. Four-membered ring over there. So you will get this compound. Whether the reaction will proceed further or not? No, because now there is no alpha hydrogen in this alcohol. Now we'll discuss the another reaction, the oxidation of the aromatic hydroxy compounds. Oxidation of hydroquinone system. Oxidation of hydroquinone system using lead tetraacetate. What is hydroquinone? This is hydroquinone. So upon reaction with lead tetraacetate, it is changed into benzoquinone. Benzoquinone. Whether this species, whether has it undergone the oxidation or not? Yes, it has undergone oxidation. If you calculate the number of hydrogen in the starting molecule and in the final molecule, you will see that the hydrogen content has now reduced. So the removal of hydrogen is known as oxidation. So hydroquinone now have oxidized into quinone. Let's see how this transformation occurs, how this oxidation occurs. This is another application of the lead tetraacetate. What happens? Mechanism. It attacks on this lead, then one of the acetate ion leaves, you get this. Oxygen is now bearing positive charge. When this oxygen attacks on this lead, acetate ion leaves, oxygen gets positive charge. So how this positive charge will get be stabilized? When this deprotonation will occur and this bond will move here and the hydrogen ion leaves from this way and acetate ion leaves from this side. So the actually the leaving is the acetic acid. You will get this molecule. Now what happens in the next? So I should write it here. In the next step, when this lone pair moves here, this bond moves here, and this moves bond moves here and this way. Acetate leaves. How many arrows are there? No, 5 arrows. Look. When the lone pair it moves here, making a new bond between carbon and oxygen, double bond. This bond moves here, this double bond moves here, making a new bond between carbon and oxygen. This bond moves here, this bond moves here. So you get this species. An acetate which is leaved from this intermediate, and in the next you get deprotonation, this hydrogen ion and this acetate the leaving acetate both form acetic acid, and finally you get this hydroquinone, sorry, benzoquinone. What was our starting molecule? The starting was the hydroquinone. So hydroquinone, upon reaction with lead tetraacetate, it undergoes oxidation and it changed into benzoquinone. I have explained the mechanism. I am writing two important problems for you. Try it by yourself. You will have to practice the mechanism by yourself. This is another hydroquinone type system. Upon reaction with lead tetraacetate, what will be the product? And you will have to write the mechanism while solving these problems. It's the same like hydroquinone. So when hydroquinone react with lead tetraacetate, it forms benzoquinone. You will have to write the answer of this reaction, and also you will have to show the which mechanism does it follow. The same way I'm giving you the hint. First try to react with one of the hydroxyl group with this lead tetraacetate, and then try to rearrange this bonds, delocalize these pi bonds, you will find the answer. I'm writing another problem for you. Try to solve it by yourself. Here we have another hydroquinone system. Upon reaction with lead tetraacetate, this part of molecule, it will undergo oxidation. Hydroquinone system is there, so it will be changed into benzoquinone. Write the structure of the product and also explain it with mechanism. I'm sure that you will solve it easily. Oxidation of 1,2-diamino compounds using lead tetraacetate. Now let's discuss another application of lead tetraacetate. So dear students, what are 1,2-diamino compounds? Sorry, NH2. The same way that we studied 1,2-diol system, these are 1,2-diamino compounds. So upon oxidation with lead tetraacetate, tetraacetate oxidize them into 1,2-diimines. 1,2-diamino. So these are diamines. 1,2-diamine. And what is this? 1,2-diamine. These are amine. These compounds are called amines. How this oxidation occurs? Whether this compound has undergone oxidation or not. Yes, it has undergone oxidation. Calculate the hydrogen, number of hydrogen in the starting and in the final product. You will see that the hydrogen contents now has reduced. The removal of hydrogen is called oxidation. So let's see that how this oxidation occurs. It attacks this lone pair of nitrogen, it attacks through at this lead, and this acetate ion leaves. The same way this attacks over this lead and acetate ion leaves, and then deprotonation occurs and you will get this intermediate. I'm sure you can easily reach on this intermediate. I'm repeating for you that this amino attacks on this lead through this nitrogen, lone pair of nitrogen. First this nitrogen will get positive charge, and when deprotonation will occur, so it will stabilize its positive charge. Acetate ion leaves here. The same way the other part will react. So there will be two molecule of the acetic acid, they will leave, and finally you will get this intermediate. In the next step, this intermediate is cyclic ring, it ruptures. How? Like this. When this bond moves here and this bond oxidative cleavage occurs here, and this bond moves here, so you will get this compound. Two molecule, because the since we have the similar type of structure here, so two molecule of the amines are obtained. uh, I have shown here, I think, a wrong structure here. The oxidative cleavage occurs here, so I should write, I'm going to correct myself. Two molecules of the amine will be formed, not this. Cross it. I'm writing here and other diamino compounds, and both are vicinal to each other. Upon reaction with lead tetraacetate, they undergoes oxidation, and you will get amines. This is very another important example of the if the two amino groups are adjacent on the over the aromatic ring. Upon reaction with lead tetraacetate, they undergo oxidation, and finally you get nitriles here, dinitrile. You can also write it like this: CN, CN. I'm sure that you will be easily able to solve the mechanism. Okay, I am going to solve this mechanism for you here. Mechanism. First, these 1,2-diamino compound upon reaction with lead tetraacetate, there will be the formation of this cyclic intermediate. In the next step, this cyclic intermediate, it rupture, this bond moves here, and this bond moves here, and this bond moves here, and you get this compound. OAC, lead acetate, and two molecules of the acetic acid will also be formed. This we will get, the reaction does not stop here. It reacts with another molecules of the lead tetraacetate. It attacks here, and acetate ion leaves. This lone pair attacks again, and this acetate ion leaves, and deprotonation will occur. So two molecules of the acetic acid will leave, and you will get this intermediate. You will get this intermediate. What will happen next? The rupture of this intermediate. When this bond moves here, it moves here, and it moves here. So lead acetate, not tetra, lead acetate. One molecule of the lead acetate is formed, and the cleavage occurs through this carbon-carbon of this carbon-carbon single bond, and you will get your final product. You can write it like this. This is another application of the lead tetraacetate. So if the two amino groups are the part of the aromatic system, then the final there will be cyanide groups, or the nitrile group would be there. If the two amino groups are the part of the open chain or the cyclic compounds, like this, if the two amino groups are the part of the cyclic system, then there will be the cleavage of the carbon-carbon, oxidative cleavage of the carbon-carbon bonds of the two adjacent carbon atoms which are bearing these two vicinal amino groups. And if these two amino groups are the part of the aromatic system, then each carbon will change into nitrile. I'm sure you will get this point. The last application of this lead tetraacetate is the decarboxylation of dicarboxylic acid using lead tetraacetate. So let's, if you have, suppose you have this compound, upon reaction with lead tetraacetate, decarboxylation occurs and you get this compound diene, and two molecules of the carbon dioxide are also formed, whether this compound has undergone an oxidation or not. Yes, it has oxidation. The number of hydrogen in the starting compound are reduced in the final product. So oxidation has occurred using lead tetraacetate. Now let's discuss its mechanism. Lead tetraacetate. In the same way as the 1,2-diol reacts, consider these two hydroxyl groups as a diol. How it would react? This lone pair will attack here and this acetate will leave, then deprotonation will occur to stabilize the positive charge. The same way this part of the molecule will react, the hydroxyl group through this oxygen, it will attack on this lead, acetate ion will leave, and this oxygen which previously would got positive charge, when deprotonation will occur, this bond will move here and it will get stabilized. So finally you will get this intermediate. You will get this intermediate, and this cyclic intermediate in the next step it will undergoes the rupturing. When this bond moves here, this bond moves here, and this bond moves here, and this. So you will see that you will get carbon-carbon double bond here. When this bond moves here, making a carbon double bond oxygen, so one molecule of the carbon dioxide from this side and one molecule of the carbon dioxide this side, they are formed, and you will get lead acetate. Do you see that how this decarboxylation occurs? The condition is that these two carboxylic groups should be on the vicinal carbon. First there will be the formation of the cyclic intermediate when this dicarboxylic compound react with lead tetraacetate, and then there will be the rupturing of this cyclic intermediate into this diene, carbon dioxide, and lead acetate. I'm writing a couple of problems for you to solve. When this molecule react with lead tetraacetate, what will be the product? Explain through mechanism. And when this molecule react with lead tetraacetate, what will be the product and the mechanism. Now let's summarize, because this was a quite big lecture. Let's summarize this. First, this lead tetraacetate, it oxidizes. Number one, oxidation of 1,2-diols, oxidation of hydroquinone systems, oxidation of 1,2-diamino compounds, whether they are part of the aromatic systems or the part of the open chain system, decarboxylation, and oxidation of alpha keto acids. So upon oxidation with 1,2-diols, the oxidative cleavage occurs and dicarbonyl compounds are formed. When hydroquinone system reacts, then benzoquinone type compounds are formed. When 1,2-diamino compounds, if they are the part of the open chain or the cyclic systems, then diamines are formed. If they are the part of the aromatic system, then nitriles are formed. If the decarboxylation occurs from the bis dicarboxylic compound from the same site, then alkenes are formed. And when alpha keto acids react, then also carbonyl compounds are formed. So thank you so much.